We are going to learn how to do more derivatives of more complicated functions. And we have a new rule. We've done the product rule, we've done the quotient rule. Now we have a chain rule. Okay, well, the product rule is obviously for when two functions are being multiplied together. The quotient rule is when you have a function being divided by another function, or a rational function, okay, composed of two separate functions. Another function operation that you've done in the past is composition of two functions, like f of g of x. So a function within another function, okay? And that's not multiplication. Very important for you to understand that. That is not two functions multiplied together. It's an entire function within another function, okay? And in order to do the derivative of the composition of two functions, we have what's called the chain rule. The proof of the chain rule is on page 131. You're not required to know the proof. It's a little bit more complicated. I'm not going to go through it with you at all. But if you want to look through that, it's on page 131. Okay. But the chain rule is what I'm going to show you today. Okay. Chain rule does get its own standard, it looks like, from looking ahead at a few of the next tests that are written. C8 is specifically chain rule derivatives. Okay?
Do you want to start the video now or not quite?
It is started. I thought it started.
No, I did that the other day too.
Okay.
I looked at
Good.
it. Yep.
Alright, so chain rule. Basically, the derivative with respect to x of a function being composed with another function. So if you got the composition of two functions together, alright, a function within another function. To do the derivative of that, you'll take the derivative of the function that's kind of the outermost function, and then take that times the derivative of what the function that was within the other one is. And I'll show you with an example, you'll get a little better understanding. Alright, so let's say we have this function, y equals the quantity 3x minus 2 to the 4th power. Before today, if you wanted to find the derivative of that, okay, you would have had to have actually taken this times itself 4 times to see what that is as a long polynomial, and then just done the derivative of each individual term. Okay? But a chain rule allows you to keep it in its form, not have to do that extra work, and still you're able to get the derivative fairly easy. Okay? What sometimes I kind of tell people to think, and I'll show this again maybe a little bit later, but what if this was just
x to the 4th,
x to the 4th?
and then you're essentially putting the formula.
What is the derivative of x to the 4th?
4x to the third.
4x to the 3rd, right? So I still want you to do that, just like you would there, okay? You're still doing the derivative of this function. Alright, you're doing the derivative of this function, but after you do the derivative where you kind of just pretended that was just a regular x,
Then you multiply it by what's on the
you need
inside.
to multiply it by the derivative of what you just left alone.
So 3.
So in this case, 3.
Okay.
Because what's the derivative of 3x minus 2?
3.
Just 3. I would want you to simplify that. So y prime equals 4 times 3x minus 2 to the 3rd times 3, which ends up being 12 times 3x minus 2 to the 3rd, and that is as far as I would want you to go on that.
Make us factor that.
No, I would be, that'd be a waste of time.
That's nice.
Okay? another thing that some people have thought of, or how they think of this chain rule, okay?
So this be like the final answer?
Yeah, that's your derivative. Yep. They might think of this, they might say, let u equal 3x minus 2. Okay? Let u equal what's inside the parentheses. So then, you really have y equals u to the 4th, right? Okay? So then, y prime would equal 4u to the 3rd, but because we're using the chain rule here, take that answer times the derivative of u. Some of them kind of use that as kind of like a substitution method, if you will. Okay? So then if you substitute it back in, substitute what u actually is equal to, if you substitute that back in, 4, well u is this, so 3x minus 2 to the 3rd, times, what's the derivative of u? Well, that would just be the number 3. And then again, you get the same thing. The reason that you do, you're not probably seeing the need for this right now because this one is fairly simple. But there's definitely times where people find that helpful to think of it that way. Okay? Because the book even kind of uses that definition a little bit. Yeah, that's going to be, because you're quite going to follow that one as well. But basically, they kind of use u substitution to help them do the derivative, to make the derivative seem simpler. But if you use u substitution to do the derivative, just make sure you remember to multiply it by the derivative of u at the end. Okay? Everybody got this one?
Yeah.
Let's say I got the cube root of 6x to the 3rd minus 9x.
That's the derivative.
That's the original function.
Alright.
The brain's getting ahead of
So would you put x to be, or u to the 3rd?
If you're going to use u substitution, okay, then you'd have the cube root of u. Alright, if you want to do it that way. A lot of people, if they're not using u substitution, might write it like this first. 6x to the 3rd minus 9x, and then all that raised to what power? The 1/3 power. So they might rewrite it with a fractional exponent first, and then use the chain rule from there. Again, if people are using u substitution, they might say let u equal 6x to the 3rd minus 9x, and then really my function, my original function is simply u to the 1/3 power. Okay? I'm doing this two different ways. Everybody understand that?
Yeah.
Okay. The brown is doing it one way without u substitution. The blue is using u substitution, whatever way makes the most sense for you. Okay? So then if I was following this way along, alright, f prime of x, again, I just kind of pretend what's in the parentheses is just a variable, so really I just have x to the 1/3. I'm really doing this, in a sense, but I'm just not writing it that way. Okay? I have something being raised to the 1/3 power. To do the derivative of something raised to the 1/3 power, I got to bring the 1/3 out to the front, keep this the same, and raise it to 1 less power. Okay? So that would give me 1/3 times 6x to the 3rd minus 9x, and that'd be to the negative 2/3 power. But then you do need to take that, if you remember, you do need to take that times the derivative of what was being composed, or what part was, composed into the other function. And in this case, that would be 18x squared minus 9.
Can you leave it like that?
Um,
That's not gonna be pretty.
Kind of messy.
Well,
I want you to see how it simplifies.
Oh. Actually,
it's not bad, but.
Won't be that bad.
it'd just be
18x squared minus 9 would be on top. 3 would be on bottom. That 3 from the 1/3.
Mm-hmm.
And then you'd have the cube root of 6x to the 3rd minus 9x squared.
Are you
Do you
saying,
guys see that?
are you saying that it's 1 over what's on the left side then?
Where now?
Like, oh, never mind, I see what my,
Do we have
never mind.
to do that?
Yeah, do we have to do that last time?
Okay. No, that's probably fine. Understand, I guess if the directions would say no negative exponents though, you have to move it. I don't care necessarily about putting it back into radical form. Understand that if the original problem had a radical in it, the answer in the back of the book that you're checking is probably going to have a radical in it, because if you start with radicals, you usually end with radicals. Okay? But everybody understand why this goes to the denominator.
Mm-hmm.
You have a negative exponent, move it down to the bottom where it would become a positive 2/3 on the bottom, and a positive 2/3, as far as an exponent is concerned, is the cube root of that something squared.
Mm-hmm.
Okay? So that's what it would be there. Again, that's going to be very similar. Some people just don't like writing it out. They like doing the derivative of this very simply to start with. Because, yeah, go ahead.
Could you divide the top by 3 and just get rid of that 3 out front or no?
Yeah, could you simplify it further? I would argue, yeah, you could. Great, I didn't even see that right now. Good, Grace. You said the bottom is divisible by 3 and the top is divisible by 3. So really you could have 6x squared minus 3 over the cube root of 6x cubed minus 9x squared. So yeah, that's true. I bet in this particular problem, if this was the problem in the textbook, this is what your answer would look like. Going back to u substitution, okay, a lot of people like it because doing the derivative of u seems very simple. So f prime of u would equal 1/3 u to the negative 2/3, but then just don't forget the times du. And then substitute back in. So 1/3, replace u with what you set it equal to, 6x to the 3rd minus 9x, that's raised to the 2/3 power, times the derivative of u. So the derivative of u would be 18x squared minus 9, so 18x squared minus 9 would go right there. And you got to the same place as we did here.
For you, could you simplify it and then plug it back in? Would that work?
For you. Oh, could you simplify at this step? Yes.